Without further ado, I want to introduce Professor Khalil for his talk. I don't know if I think you can share your screen because you are a co-host. Professor Waleed, can you hear us or can you still there?
Yes, I'm just trying to share the screen.
Okay, while you're doing that, let me just introduce you and give a quick background. Professor Khalil, Waleed Khalil, he received his PS and MS degrees from University of Minnesota and his PhD from the Arizona State University. He's currently serving as a professor at the ECE, Electrical and Computer Engineering Department, and ElectroScience Lab at the Ohio State University. He also serves as the co-director of the Air Force Center for Excellence and for enabling cyber defense in analog and mixed signal domain, and National Microelectronics Security Training Center. Prior to joining OSU in 2009, he spent 16 years at Intel Corporation, where he held various positions in research and product group. His group's research is focused on integrated circuits and systems with applications in the area of hardware security and trust, wireless and wireline communications, heterogeneous chip integration, and image sensors. He is a recipient of OSU's College of Engineering Lumley Research Award and IEEE ETA Kappa New FED Fred H. Distinguished Teacher Award. His research group has received several Best Paper Awards and Distinguished Teacher Award and in several conferences. He authored 19 issued and several other pending patents, over 120 journal publications and conference papers, and 3 books and book chapters. He served as the associate editor for Journal of Solid State Circuits and is currently serving as the associate vice president for publications at the IEEE Solid State Circuits Society and co-general chair of the IEEE International Symposium of Hardware-Oriented Security and Trust. Thank you, Professor Waleed, and looking forward to hearing from you.
Thank you very much, Professor Musa, for the introduction, and good morning, everyone. And thank you all for tuning in to my talk today. Can you see the slide?
Yes.
Yes.
Okay, let me go back again here. Okay, so I guess we all know, like today, how much the advances in microelectronics have changed and will continue to change our world. And we felt that dearly when, COVID struck and we saw exactly how much impact it had on us. However, the advances that we have today in microelectronics also come with kind of a set of its own challenges, particularly in the realm of securing that microelectronic device and the supply chain hand in hand. Much of the focus today has been more or less put towards the digital realm of security. But I'm here today to give you kind of a bit of an outlook of how much we need to think about the analog domain as another domain that we can exploit to secure our microelectronics and make it trustworthy. In the talk today, I hope that I will explore some of the progress that we've made in our research in the center in complementing the digital domain and establishing kind of like a more trustworthy and resilient hardware platform. So with that in mind, let's go ahead and dig into the talk. So looking back, over several decades now, the integrated circuit design has been more or less developed with assurance in the terms of how can we make the circuit yield better in that case. So in this way, if you go back to the early 70s, the industry started to adopt several key milestones, as I listed here in the chart, starting with built-in self-test, and then adopting a scan chain test, and then later on building in a wafer sort capability so you can sort the wafers before you basically decide to ship them out. Then built-in self-test started to emerge to make sure that you test before, again, you package. And then later in the early 2010s, we started to see thermal sensors being everywhere. And, you know, all of you have laptops, computers. You see that when the thing heats up, it just shuts down. So that was a safety measure to make sure that the device continued to work after it shipped. And then just lately, in the 2020s, we started to see the notion of what we call silicon lifecycle management, which means that if we ship a product today, I want to make sure 20 years from now, if it's deployed into the field, that I'm monitoring and I'm adapting to what's happening with that product to make sure that it functions as intended. However, if you encapsulate all of this, adaptation of changes that happen or deployment that happened in the microelectronics to try to improve the yield, the industry has been very much focused on issues related to manufacturing problems, things like wafer defects, lithography problems, doping variation, if you have any contamination, or even post-manufacturing issues, things that happen after you actually ship the product. With that in mind, here, we've seen a lot of the focus in terms of assurance to be more on the physical and functional aspect of the IC, which is how can we make it perform according to what is intended. With that, we cannot just think about assurance in this way. We have to also think about assurance, not just from a quality metric standpoint of view. The industry started to think about assurance from a security standpoint of view and what are the security implications when we deploy the microelectronic device. So this kind of thought towards embedding security as part of your quality and assurance part of your design is only about 10 years to 15 years old. So that thinking of maturity started to happen 10 to 15 years ago, where people started to see that, you know, we have to really think about security as an issue that is, we basically didn't have to worry about it before. So it's not just how good the chip is going to perform, but how it can be protected, either protecting itself or protecting somebody who's using it from making sure that an external threat doesn't get into the integrity of the entire system that realizes this chip. So with that, let's just talk about a little bit what is the security aspect that we see happening here in the integrated circuit and how it evolved over time. When we talk about security, we start to see that we encounter a new set of challenges that are as demanding, if not even more demanding, than those that we highlighted when we talked about quality assurance before. The first thing that we started to see as a major problem is we don't have really a comprehensive verification method. It's very easy to measure functional quality because you can really set the bar and say, you know, is the part performing or not performing? And you have very discrete way of measuring that. When you talk about security verification, we don't have a comprehensive method even today to be able to tell you if this device is secure or if it's not secure, if it's secure enough or it's not secure enough. And this is very concerning because without proper verification, we cannot confidently say or answer a question whether this device has been can be deployed in a secure environment or it cannot. So with that, we need to answer some questions about the manufacturing aspect of this device. Do we know, has it been manufactured in the intended place that we fetched the device from, or it was sourced from another foundry and then basically packaged or remarked or whatever to be the part that is intended? We would like to get a notion where we can identify every part in a standalone way so that we can establish provenance of that part. And finally, we'd like to see after manufacturing, did somebody actually, through the manufacturing supply chain, was able to tamper with that product and alter the functionality of the product. Now, why do we worry about that? Because the attacker space has been increasing exponentially over the last 10 to 15 years. And we're seeing every day new emerging threats that are really something would have been a dream if you go back 10 years ago in the industry. And that calls for an urgent call of action that we need to think about. So we also need to kind of acknowledge that when we think about a semiconductor device today, we have a very complex global supply chain. And the chip that we have in our hand have traversed various geographies before it reaches the intended destination. And the distribution market that we have today, the network that we have today, can expose the chip to a multitude of tampering risks throughout the life cycle. From the moment they are basically conceived in the design, when you actually build the design, all the way to the field of deployment when you actually have them at the end of the supply chain. And I give you an example that, Trojan insertion or backdoor vulnerabilities, alteration that we have in a foundry, fault injection attack, all of these are possible that can happen throughout the supply chain. That's why we need to think about a way that we can continuously monitor the device that we have in hand, not just test it after it leaves the foundry, but throughout the deployment phase, we have to have a monitoring method to observe the device and assess the assurance aspect of it. So the industry started to pay attention to that. And in the early 2000s, the notion of what we call physically unclonable function started to emerge as a pillar for security assurance. So let's kind of, for people who are not really aware of what a PUF is, let's kind of dig a little bit deeper to understand what a PUF is. So a PUF basically is a way for you to exploit the variation that you have in the manufacturing process of semiconductors today to create a unique ID, you can think about it, that is more or less constructed by what we call a challenge response pair, meaning you can think about it that way, like a secret word. If I basically ask you a question, you need to answer back with an answer that I expect you to answer. Now, if there are so many unique questions, there will be so many unique answers. Very similar to what you have today when you basically, they ask you to put 3 questions to authenticate access in a website or something like that, except that the challenge response pair for a PUF, because of the amount of chips that we have shipping or coming out of a foundry can be in the billions, is going to be enormous amount of database that we have to keep track of. Now, with that in mind, this PUF notion can give you a unique ID that every die that we have coming out, or every chip coming out of the foundry, we can quiz it and basically extract the ID that is specific to that particular chip. And then we can compare it with our database and say, this is actually a chip that belongs to our database, and we can confirm that it came from that particular foundry, or we don't. The problem with PUFs, there are a few things. They give you the added benefit of IDing the chip. The problem is, as you can see here, as you increase the number of chips coming out of the foundry, that database is going to be enormous to keep track of. And that can be also very expensive and very costly when you think about it. The other problem that you have, you can think about the PUF like a serial code. If you have a serial code or a barcode that is attached to your box of cereal, I can take the same serial code and I attach it to a can of tuna. Now, that doesn't tell you much whether this came from a foundry that manufactured the serial code, the cereal box, or the one that manufactured the tuna. So the uniqueness in the PUF is in that serial code, but that serial code can be lifted off or can be replicated or can be forged so that you can actually end up falsely identifying the part because of that. And there are a lot of attacks that people have envisioned over time, and particularly on PUFs, to try to basically forge the ID, like similar to what I described here. Finally, it doesn't also give you the origin of the manufacture, what we call the origin of the manufacture, because it's like a barcode. We cannot tell whether this came from that particular foundry or it came from a different foundry in there, or from which fab within the foundry. TSMC have almost 30 foundries today. Which one of those did this device come from? If we would like to know that, we don't have the ability to do so. And then, since the buff is localized in a given area on the chip, as highlighted in the gray here, it only gives you identification relative to that part of the chip. So if somebody was able to tamper an area around the puff, outside of the puff will not be altered in functionality, and therefore you cannot predict the tampering part of that. So that's the advantages and disadvantages of the physical unclonable function. A couple of examples of puff that are basically in deployment today. That probably the left one is the most famous one, what we call an SRAM puff. And the idea here is to have the SRAM, when you power it on, a lot of the SRAM cells will default either in 1 or 0 in a default manner because of the variation that you have. So this is without even loading any data into the memory. You will see that the data, that memory carries data. Now that data is very unique to a particular chip. And then if you measure that data for every SRAM, you can more or less establish an ID based on that puff. Second example of that, of what we call a ring oscillator puff, where we can exploit many parallel ring oscillator timing variability because of the process variability that we have. You will have a very different frequencies that come out of these ring oscillators. And if you basically can compare them with each other, you can actually come up with a very unique set of an ID that you can, again, identify that one part relative to the other. So with that in mind, the industry kind of evolved into 10 years after into a different type of an assurance identification method, which we call a process characterization function. And a process characterization function, again, leverages the unique characteristic that we have in each foundry. And from that on, we can use that to differentiate the origin where that particular chip has come from. And you can think about that as a way for us to identify the unique traits of a given chef's recipe. If you have a chef and you'd like to replicate or identify his or her recipe, there are certain things that every chef has, which is, you can think about the secret sauce, that we can basically identify that this particular meal came from that chef. And with that, we can say that this particular chip came from that foundry. Now, every foundry has very different process steps and parameter setting, and that creates a distribution of variability that is very unique from foundry 1 to foundry 2. Since that distribution of foundry dependent parameters is unique to the foundry, it's a very small set of database that we can keep track of. And if we're able to measure our parts and fit it within one distribution or the other, then we can identify that this part belonged to foundry A or foundry 1 or foundry 2. And the beauty about it, unlike the puff, that this database is independent of the number of the chips. As we said in the puff, the challenge response pair database grows linearly with the number of chips that were produced from the foundry. Here, that distribution is only related to the foundry parameters, not the die itself. However, this has the positives of what mentioned. Some of the drawbacks is we are able to identify the origin of manufacturing of the part, but we are not able to identify each part uniquely by itself, which the puff would have given us in this case. Also, similar to the puff, because whatever that we're going to use to identify and measure that foundry parameters is a block that is somewhere going to be on the die. And the problem with that is that if any type of alteration that happened in the design or in the foundry around that highlighted area, we're not able to protect again. So we're not able to see tamper that happens outside of that grayish area that we're highlighting here. So there are a couple of designs or a couple of ideas that people conceived to build what we call a process characterization function. The one on the left, basically they build an A to D converter, an analog to digital converter, and then they measured the capacitor variability that we have in the process, and they establish a distribution of these capacitance, and that basically fits to a given foundry distribution. From there, they're able to identify the foundry. Now, of course, you need to build an A to D converter and have the complexity of that. But let's say you don't have the ability to build a BD converter, you work in a memory process, you have a DRAM process. So again, they came up with the idea of utilizing the read access information of a DRAM, where when you actually start to read from a DRAM cell, you issue a control signal, an activation command signal called an ACT, to activate the word line for that particular row that you're going to read. Once you charge the row, the controller starts to issue a read command. Now, there is a minimum required time between when you activate the ACT command and when you activate the read command to read the information from the cell. We call that activation latency in an SRAM word. If you cut that latency down, you start to get a lot of errors in the read. Now, that variability of errors that you get is very unique to a particular DRAM foundry. If you can ever read that information, then you can identify DRAM foundry A from DRAM foundry B using this method that we have in here. So let's summarize the two approaches that we talked about in here. We have the PUF approach. We can obtain die identification. However, we cannot authenticate the origin of manufacturing of that part. We cannot also detect tamper detection. And we have the process characterization function, which gives us the ability to do a die authentication, origin of manufacturing identification, but it does not give us a die unique ID that we can identify the die like the PUF does. And as well, it doesn't give us the tamper detection. So with that in mind, we started to think about a way that we can build a different type of approach, that can give us everything under the hood here that we'd like to establish for chip security and assurance. And we started to think about, how about if we look at the manufacturing process that we have today and look at the metallization that sits on top of the chip, which basically all the routing of signals that happen, whether it is signals or power or ground, happens on that layer. And this is what we call a back end of line part of the chip fabrication process. Now, if you're able to build a sensor that can measure the characteristic of that back end of line, then you can have a lot of positives that we're going to go through here that you can get out of it. The first thing we started to see is that this foundry and foundry B will have a completely different set of back end of line processing. And therefore, if you're able to measure that back end of line characteristic, you can basically identify the origin of fabrication of that device. Now, also within the foundry, there is variability that you have in that metallization routing in terms of the resistances and capacitances. And these uncontrollable process variation can be exploited so that we can build a unique ID for each device that we measure the back end of line characteristic out. Now, if we're doing a sensor, we can build it on chip. If we build it small enough, then we can distribute it, as I'm showing here, everywhere around the die that has the back end of line routing. So anywhere, routing is everywhere on the chip. If it's small enough, we can embed it basically and repeat it over many, many areas within the die. And that will be very low cost and doesn't require any extra processing chip. Now, because it's distributed all across the chip, if you start to tamper with the die, basically tampering, that means you're going to try to open up the die somehow. You're going to alter the characteristic of that metallization. And once you do that and you use your sensor, you can basically detect that a change has happened, and therefore you detect the tamper or a Trojan insertion that happened because of that. So that's basically the nutshell of an idea that we started to embark on almost 5 years ago. Now, when we started to look at, the question is, how can we build this sensor to be small enough and yet easy to deploy and give me an accurate information that I can identify exactly what is the characteristic of the back end of line. So the back end of line is basically a set of metallization which have resistances and capacitances. So our first thought, we said, if you multiply the R times C, you get a time and what we call the time constant. If you're able to measure the time constant accurately, then you can identify basically a routing set of metallization that you can construct as a cell and then measure the RC time constant of that cell. So the idea here is if you charge the capacitor that we have, let's say we charge the capacitor that we have to a voltage V, and you basically disconnect the switch, you'll start to see that the RC of that capacitor will decay over time. And then we can establish two cut-up zones, you know, the voltage that you start with and the second voltage, which is half of that voltage. And then you can, from there, have a set of equation simply telling you that the time it takes you to go from V to half V, that time is proportional to the time constant of that metallization that we have in here. Hence, the circuit that we built can be looking something very simply like this, with a comparator that we put around to detect the voltage drop that happens when we reach the threshold of V over 2. Once we reach that, we basically dismantle the operation, and then we detect the time it took to do that, and that we correlate to the RC time of that metallization. So that's basically the idea simply. Now, when we initially start to look at this, is a very analog approach of measuring the RC time constant of the chip, which is simple but has some drawbacks in there. The first drawback is we cannot really integrate this very easily with other design. It needs a lot of what we call analog expertise. We cannot mitigate it or migrate it, sorry, to other technologies. If we have it designed in one technology, you know, you have to redesign the analog cell again in a different technology. It doesn't scale with technology. So if we go from 22, let's say, to 14 nanometer, then we have to redesign it again from scratch. It's not something that you can automate within the automation or the CAD automation tool that you do today in the design, so that you can basically insert it, as I mentioned, everywhere you have room in the design. Therefore, we started to think about, can we come with a more digital-centric design that can address the issues that we have here in the analog sense. So that's basically the idea that we started to look for, is how can we do this, but more, you know, looking at it from a digital-friendly design rather than in a comparator and all the analog analog approach that we adopted before. So to do that, the first thing that we have to look for is how to move that voltage domain measured comparator that we have here to a digital circuit. How can we do this in there? So with that in mind, we look for utilizing, instead of using an analog comparator, if we can take the voltage that we have here and convert it to a time pulse, what we call a pulse generator, and we can correspond that pulse duration to that voltage amount, then we can use a simple counter, which is a digital block with an external clock, to measure the duration of that pulse. And once we do that, we can basically, and by measuring the count of that counter, we can correlate to exactly what is the voltage that was measured from that comparator. So we shifted the design now from an analog voltage comparator to a pure digital based design that we can utilize here to do the measurement. So with that, we come up with the architecture that we have in here. we needed to generate two proportional voltages, if you recall, V1 and half, V and half of V. To do that, we have to add a current source that we have on the top here to create that. And then once these voltages are created, we convert them to the pulse with the shaded block that we have in the schematic here, and then quantize them using the counter, and then measure the count, which tell us exactly the time of, or the RC time of that cell. So this basically is, in a very simplistic way, the architecture that we adopted. I will keep it a little bit brief here to avoid overwhelming you with a lot of the architecture and technical details of the circuit that we have. Now, this all looks great. You start to basically conceive the idea now and put it in actual transistor design, and you realize some problem, which is basically defeating the purpose of what you're trying to do. Well, in any process technology today, the metallization is designed to be of low resistance and low capacitance, because everybody would like to reduce the routing parasitics, and it impacts on the timing of the chip, so we can have the chip run faster. So if your goal is to minimize the R and the C of the routing metallization, that means that the RC time constant that you're going to measure, which is R times C, is going to be extremely small. And if you're using what we talked about here of using a clock to measure that RC time constant, then you will need an extremely fast clock if that RC time constant is very small. So let's put some numbers here to give you kind of a feel of what this. Assume that we have a routing cell block that has a metal resistance in the order of 6 kilo ohm and a capacitance of 1.5 puff, and assume that we measure using a readily available clock on the chip that has a 500 megahertz frequency. And if you do the analysis, you will see that because of that clock finite duration, you have what we call a quantization error in time, which means that RC that we have, which is a 6 kilo ohm times 1.5 picofarad, when you measure it, you will end up with an error of 22% of that RC time constant, which is of course unacceptable in terms of accuracy. That's too much of an error that you are willing to adopt. Okay, so you have two options. You can grow the cell size to make the R and the C bigger, and of course that will eat up a lot more die area for each sensor. Remember, we wanted to replicate them everywhere, and that's not something that when you commercialize this, people will adopt. So you're kind of stuck in a way of how can you do this quantization in time and reduce that error that we have here significantly from what we have. So to solve this problem, we deployed what we call testing aids in the form of, instead of just only measuring the R of the metallization and the C of the metallization, every process today have what we call intentional polyresistors and MEM capacitors that are used to basically draw or implement a resistor and a capacitor outside of the metallization. The beauty about these elements that we have them is that they are what we call a high density cells, which means you can have a very high resistance within a very small area footprint. We can have a very large MEM capacitor within a very small area footprint. This is very different than the routing metallization. Now, we can use these elements along with the metallization routing to amplify the resistance and the capacitance of metallization routing, and hence we can reduce the quantization error. So here we came up with the idea of deploying 3 sets of distinct measurements that we do to measure the metal of the capacitance with the summation of the poly resistor and the metal resistance. That's one measurement, followed by another measurement where we measure the metal resistance with the summation of the metal and the MEM capacitance. And then finally, we do all in all, we measure the summation of the metal and the poly resistance with the metal and the MEM capacitance. So you have 3 distinct measurements. From there, you can deduce the R metal and C metal, which what we had before. And with a 25% increase in the area, we were able to bring down the error that we had before by 82%. So taking a small hit in area of the cell, we're able to bring down the error significantly using this measure. So this is what we adopted in the sensor. And then we fabricated this sensor in Global Foundry 130 nanometer process. And here we show you the dye photo that has an array of this time sensors of various sizes of metal resistance and capacitance. Namely, because we wanted to get a good distribution of it, we deployed half the resistance intended and double the resistance, and half the capacitance intended and double the capacitance. And then we combined them into, you know, a permutation of resistances and capacitance that we measure, and we basically replicated that in many areas on the die. So we can get a good distribution in there. Now, these sensors were repeated, as I mentioned, were about 20 sensors per each. So there's a lot of data to be collected in there, and we intentionally did that so we can basically measure a distribution rather than a pinpoint measurement. In addition, we started to look at the design. This is an in situ measurement. The problem that you have is that the process simulation files that you have from the foundry does not capture accurately the metal resistance and capacitance. As a result, if we do the measurement, there's no way for us to quantify how does this measurement in terms of accuracy correlate to the actual resistance and the capacitance of the metal on that particular die that we measured. In order to solve that problem, we basically created what we call a direct measurement array of resistance and capacitance, which is basically not an RC time constant sensor, but just a pure R and a pure C that we can measure using external test equipment and get a very accurate measure of the R alone and the C of the metallization alone. And this is kind of briefly what we did to measure the resistance of the metal directly. We basically force a current through the resistance using an accurate voltmeter off chip. And then from there on, we can calculate what is the resistance of that metal resistor that we have, that we measured. On the capacitance side, to directly measure the capacitance, because we're dealing with very small capacitance and the error in the range of, you know, femtofarads that we'd like to measure, you cannot really use external C meters to do that. So you have to basically build a circuit that we devised here that basically more or less it's a pulsed circuit that you charge and discharge the capacitor, and then you measure the average current using an accurate current meter off chip, and from there you can calculate what the capacitance of that metal is. With that in mind, the direct measurement array, we measured, as I mentioned, 3 sets of resistors, the half R, HR, and the R and the 2R. And here I'm showing the plot of the measurement from 2 wafers that we characterized with 3, 6, and 12 kilo ohm respectively. The 2 wafers were provided to us from the foundries. There was a lot of data because we have a huge array of cells. And there here we're plotting basically the distribution that we got. Notice the first wafer that we have shown kind of like a bimodal shape in the histogram. And that is because of the die-to-die variation of these resistances and relatively small sample size. I'm sure if we increase the sample size of that, you will see that the distribution is expected to converge toward the, you know, normal or Gaussian distribution that we expect to see for that. Now, the second wafer had about 10% elevation in resistance, in the mean resistance, compared to the first wafer. And that, again, told us that there is a significant process variation in the foundry of that metal resistance that happened wafer to wafer in there. Now, if we compare this result to the circuit simulation in the typical corner that we have from the foundry, we see that the wafers display on average 22% higher resistance than what the simulation model file have given us. So if we wouldn't measured the resistance using the DM array and only relied on simulation, then our sensor that we are deploying on the chip would have given us a very large discrepancy with what we have in the simulation. And this emphasized basically the value of using this direct measurement array to measure the resistance of the design. On the capacitance side, again, we have an array of half capacitance, the capacitance C and double 2C in with the range of values between 0.7 to 1.4 to 2 picofarad. And here you can see that the measurement of the capacitance show actually a very nice Gaussian distribution. And the capacitance value that we measure, the mean value, matches very closely what we see in the circuit model or the simulation file that we got from the foundry. And compared to that simulation model, the error that we measured in capacitance was 2.5%. So that told us that the capacitance parameter is a much controlled parameter in that foundry of the metal relative to the resistance, which showed a very large variation compared to the simulation file. And finally, the actual sensor intended results, which is, the RC and measuring it with the in situ sensor that we have. We show here the result for the 5 different variants of RCs that we have in the sensors. And this is across the 2 wafers that we measure. Basically what we're showing is the distribution of the discharge cycle, which is the amount of time clocks that we measured in there. And it shows consistent result across the wafer, with the second wafer again exhibiting a higher RC time constant relative to the first one. Again, we already verified, because when we did the R alone direct measurement, we saw the second wafer have a 10% higher resistance. So our sensor is basically validating that point. And here we kind summarize in this table the measurement result, and we compare it to what we measured from the direct measurement array. And we can see that the worst case error that we have from the 2 wafers relative to the direct measurement array is 6%. And I wouldn't call that an error, because even though we measure things in the direct measurement array, there is also on-die variation. So when you measure the RC on die, you're going to see some variation, maybe not all that 6%, but some of that error can be attributed to on-die variation, not attributed to our actual sensor measurement error itself. So with that in mind, we started to think of the next step. Can we do better? Can we do something a lot more integrated and smaller and easier to implement than what we did in the first proof of concept generation 1 that we have in here? So far, we realized that we had, in order to derive the R metal, C metal time constant, we had to do a 3 measurement step, which required additional RC elements and also required a 25% area penalty. We deployed a current source, which is very much an analog cell, to generate the voltages that we needed. And then we also relied on the system clock, and we said, if we need to improve the timing resolution, we need to have a much farther clock, which is a problem when you think about it for legacy technologies, old technologies, because you don't have the capability to do a gigahertz or a multi-gigahertz clock like advanced node does. So if you want to implement this in legacy nodes, we will have a problem. Our second generation time sensors basically does measure the R and the C metallization time constant directly without the testing aids that we had before. So that's the first thing that we've done, is to eliminate that, and also will make the area footprint much smaller, as you will see. And in order to rely on the clock to derive the timing of the or the timing resolution, we basically use the ring oscillator, which basically down to 1 inverter delay of accuracy in the process to more or less measure the timing resolution of the pulse that we have in there. So that gives us significantly higher accuracy in time relative to what we had before. We still needed a system clock to calibrate the propagation delay of that in ring oscillator, but again, that you can use a much slower clock to do so, so you don't really need to stress the clock frequency. We replaced the current source with a voltage source, which is, we have a voltage source connecting to the chip. And then finally, we made the design very digital friendly. 80% of the design was done using auto place and route, which means it's basically built in a pure digital flow. The only thing that is not built in there is actually the RC array itself, which you cannot, of course, it's just a set of metallization in there. So that's a very digital centric architecture relative to what we had before in the first generation. We fabricated this design in the 22 nanometer global foundry technology. And then again, as I mentioned, we relied very heavily in the digital design. And because of the approach that we did, eliminating the test aids and then also shrinking the die, we basically were able to shrink down the size of the design significantly from what we had before. The layout, as shown here, has about 49 sensors that we did, in addition to the direct measurement R and C arrays that you can see on the bottom here. And in total, there is a 270 resistor cells, 270 capacitor cell that we measure in every single die that we characterize. So the direct measurement array results in the 22 nanometer here. I'm showing it for both the resistance and the capacitance. For the resistance, the mean in the resistance is 12.8 kilo ohm, which is basically about 14% higher than what we see in the simulation model. In this technology, the foundry was very generous with us. They actually were able to provide us with what we call process control monitor, which means every time they actually have a chip on the foundry, they have basically a probe station that measures parameters on that particular die. And then they collect that for every die that comes out of that wafer lot, and they send it to us. So they give us that for the metal resistance and the metal capacitance. Now, when we compared our result with the process control monitor result that we have, we see that the foundry data itself has 10% variation to what the simulation models are, while our was 14% relative to the simulation. So the foundry data is very much correlating to what we see in the direct measurement array, which again give us confidence in the accuracy of the result. In the capacitance, the error that we see relative to the process was about 1%. And when we look at the process control monitor, we see that the error relative to simulation was 1.4%. So again, give us the confidence that we have very accurate results collected from the array. So in comparison, when we look at the two sensors that we have in here, we see the second generation of that time-based sensor eliminated the test aids, significantly reduced the area. We cut down the area by 93%. So that, you can see the significant amount of die savings that you have, which means you can sprinkle that sensor in a lot more places relative to what you've done in the first generation. And then finally, 80% of the design using a pure digital flow with autoplace and route. So here's the resolution comparison between the two sensors. And in order to compare the two, you have to think about the count, the number of counts that you can get for the same RC from one generation to the second. And you can see that the number of count on the right-hand side for the second generation is double the number of count on average from the first generation, which means roughly you have a resolution in accuracy improvement by 113%, which means you have more than twice the resolution, while you also shrank the area by 93%, which is outstanding compared to the first generation. So let's summarize where we are in our sensor roadmap. We started with generation 1. We had test 8 components, pseudo-digital architecture. We emerged in Gen 2, which we finished about 2 years ago, which has significant area reduction. We relied on the ring oscillator timing to remove the tie to the external clock, and we transitioned to a fully digital architecture. And then we are almost about to send out the fabrication of our third generation, which we've been working on since the second one. And here, the goal is to build the same sensor in different foundries so that we can really authenticate from one foundry to another. Our goal is to make this near 100% synthesized layout, which means there is no manual intervention to build this in any foundry, and also to improve the accuracy of the system while shrinking further even the size of the sensor itself. And then we are doing an RC measurement, which is a time constant. It will be really nice if we can do a standalone R and a standalone C. So we're building a standalone C sensor. And once we do that, then we can get the R also measurement result. That will give us a much more exhaustive amount of set of data on that metallization rather than just the aggregate time constant to the resistance and the capacitance standalone. And finally, which we haven't done yet, is the variability of the RC within the chip can be exploited, as I mentioned before, for die identification. So we're going to look to see what happened. Can we actually establish a die ID from these sensors? And finally, temper detection. We have some tests that we're going to do to try to basically temper into the die and measure the RC and see if there is a shift that detects that temper process. Finally, I'd leave you with a few thoughts in here is you have to think about security assurance in the way that we said in the beginning of the slides about the evolution of quality assurance today. That as we move forward, there will be a significant amount of effort that the manufacturers are going to put towards the assurance of their chips. Now, the device and process attestation that we just talked about here can give you at least a peace of mind when it comes to manufacturing provenance. And if you can add to this die identification and temper detection with a very low cost type of sensor that you can have everywhere and migrated across technologies, you can basically have a roadmap for you to solve the problems in these specific security threats. And again, we've shown that a generation of digital-friendly, low-overhead time-based sensors can actually be deployed for that cause. With that, I'll pause and take any questions that you have.
Thank you so much, Professor Khalil. Thank you for your time and your presentation. Anybody has any question? Because I have a list of questions. I have the first question I have for you, like, you know, analog innovations kind of seems to be new when it comes to microelectronics security and hardware physical security. Now, the issue is, you know, how ready is the industry for such innovations? You know, like if you look at them, they are really interesting and they have potential, but how ready is the industry for it, based on your experience?
So the industry, like, you know, I draw a thing in the beginning showing you, if I can go back here. So if you look at that, you know, roadmap for quality assurance that the industry has built. So I can give you an example that when we were doing thermal sensors while I was at Intel, we started with the idea of having these thermal sensors because a lot of the processors will overheat and then you start to see a significant degradation, which is irreversible in terms of a damage to the processor, which means eventually, you know, your processor is going to fail. And we started putting this thermal sensor, and then they were too big, they were not accurate. And over time, it took us from the time of inception, like the idea itself, to the time of being in every single processor today that ships out of Intel. There are multiple of these thermal sensors on the die. It took us in the order of 5 to 7 years of deployment. Because once you have an idea and then you want to take it on to high volume manufacturing, then there is a whole asset that you have to go through of proving the idea in a high volume and making sure that you're not getting false positives or false negative, or you're getting the correct result, etc., because, you know, you're going to rely on this post-manufacturing. So any post-manufacturing type of approach takes a lot more time to evolve. So the other example I wanted to point to you, Dr. Musa, is the silicon lifecycle management, what we call the SLCM approach. So this basically, the idea here is that you have significant amount of sensors that you have everywhere around your chip, and you're measuring any type of perturbation that happened. And because a lot of the stuff happens due to aging. A lot of the manufacturing processes today have an aging problem with it. Then you're able to adapt the chip to that aging process that happens. And because of that, you can elongate the use of the chip over a much longer time than before. That concept actually started about roughly in the early 2010s. And we only started to see coming to fruit. And it's not deployed everywhere, but it's deployed in certain design that really need that kind of monitoring. It's deployed right around in the early 2020. So almost a 10-year gap between the time that you start and the time you deployment. It doesn't mean that the idea is bad. It just means that you have to take a lot of time to perfect the idea. And that's why, when we're doing the design, Gen 1, Gen 2, Gen 3, we're keeping in mind that certain things have to happen in terms of the cost of insertion, like how small or big this is going to be, how easy it is to insert, how accurate are the results, what is the variability of the results with the environment once you are in operation. So all of these things have to be taken into account for these to be commercialized. Hope this answers your question.
Yes, thank you so much. I have two more questions. One from students, like if you want to advise the students in the room, undergraduate or graduates, how can they be ready themselves for the opportunities in the microelectronics and hardware security?
How can they prepare themselves? Okay.
Yeah.
So I have one thing for the students, maybe in general, not just related to security. Today, unfortunately, what we call a narrow focus approach to the field that we're working in is becoming harder and harder to justify or maintain. And what I mean by that is that if you study and you're saying, okay, I'm just going to be a circuit designer. I really like doing circuits and I like building chips and transistors, but I really don't care about, a statistical domain. I don't care about signal processing domain, or I care about communication domain, etc. Or I don't care about information theoretic approach, things related to information theory and the theory of cryptography, etc. The problem that you face is because of the complexity of the things that we're building today, you need to have what we call a system approach to how do you actually address this problem. And to become a system savvy person, you have two ways to do it. Either spend significant amount of time in the field working in different areas throughout the system. That can take you 20 years or more in there. And that today is unfeasible because there's not much patience to wait for that long for you to have that skill set. Or that you have to equip yourself with a latitude of skills in different areas and venture out of the area that you actually feel comfortable with. So from myself, I used to be more of a circuit designer, very much in the analog and RF. But then I started to think that, communication, digital signal processing is going to be the wave of the future. And then I started to take a lot more emphasis in the way I actually study and do research in that domain, complementing what I have in the pure circuit area. I, initially was a process engineer, even myself. So what you see here is that try to expand your horizon and don't tunnel your vision into just one specific area. Even though you are not comfortable with it, sometimes students will come to me saying, I don't like signal processing, it's too tough, or I don't like electromagnetics, it's too tough in there. Yes, you might not realize the importance of something that you take right away, but you will realize it 5 years down the road when you go into the job field itself. So that's the way I always think about it, and I tell the students is don't think of the thing that you study today as something that I have to use, and if I don't use it, this is a useless thing to do. That is not the way the world works, or that's not the way things are built today, specifically if you want to work in the microelectronics field.
Thank you so much as well. Like very nice advice, and actually describing maybe the track to many professors has gone through, given like the advances we face every day. like if we don't like pivot to new areas, we may become obsolete. And the same thing here in this area, which is continuously advancing. If we have one room for one more question, which is I have here sent to me, which is how ready are we as a nation to deal with the hardware security vulnerabilities, given to the supply chain issues and now with everything happening politically, how ready are we for this?
So we have to look at it from two different viewpoints. From a chip manufacturing point, let's say I am Intel, NVIDIA, Qualcomm, etc. I'm building these chips. You continue to see, things that you test in the lab, and you see vulnerabilities and threats in there. People report them on a daily basis. However, when you look at it from that sense, you see that even though there is a vulnerability of something that happened, it doesn't really affect the bottom line as much as I have, unless something catastrophic happens. Let's say every single Qualcomm chip that shipped in, every user of that had a timeout that couldn't use the chip for a day or something like that. That vulnerability was so bad that it halted across the nation the use of that particular chip. Because of that, and because of what I mentioned in the beginning, that security verification, like to have a metric for security, you can say that when I buy, let's say, a processor, I need to run the processor at 3.2 gigahertz. If it ran at 3.18 gigahertz, I'm not going to ship it because it doesn't meet the frequency or the clock frequency rating for that particular chip. So it's easy to validate that. It's easy to validate quality metrics that we talk about in here. It is not easy to give you the same answer when it comes to security. And to the points of manufacturing, that is making them very hard to assess how much of that security needs to be embedded into the device and how much money they have to spend on securing the chip. Now, on the policy side, the country side, as a country, we realize the problem, that there is definitely a problem that somebody in one day can completely stop everything that we work with, given how dependent we are on microelectronics, from working in there. And because of that, you started to see something that evolved. Like last year, the government adopted what we call the federal trust mark for IoT and other devices, which is basically certain rules and metric, like an ISO standard. Like if you're going to ship your product, if you put on that product the label of the cyber trust mark, that means that this product, exactly like an ISO, has gone through many steps of security assessment and verification to roll it or enroll it as part of the trustworthy IoT devices. The threat with IoT is significantly bigger than anything else because they are much smaller devices, they're a lot cheaper, and because of that, manufacturers tend to cheat. They don't want to put a lot of measure of security on the IoT. So the cyber trust mark is expected to start in 2026, late 2026 and beyond. And you're going to start to see a lot of devices now as a consumer. Some of them have that mark, some of them don't have it. And because of that, you as a consumer now will have to make a decision. Shall I buy a camera that is more trustworthy, or shall I buy a door, sensor that is more trustworthy, that has the mark, or it doesn't? As a consumer, at least you will have the notion put into the label of that part to tell you whether to buy it or not. So there is definitely forward step taken in that field, except again, it's not as fast as you expect for something that is deemed to be of national interest like security.
Thank you, Professor Khalil, for your time. I really appreciate everything you've shared with us today. We're exactly on time. I think we have no more questions. Thank you again for your time, for your presence, for sharing your ideas and your research. This is amazing. And this concludes this part of the the colloquium.